you guys. Today I want to talk to you about scientific notation, metric conversions, and dimensional analysis. But before we begin, don't forget to grab your notes, highlighters, and a pen or pencil to write with. Okay, so in scientific notation, we use the standard. So please make that correction in your notes. But we make the standard, we use the standard format. And this is how the standard format looks. So go ahead and highlight that in your notes. It's the standard format. Okay. So this right here is known as the coefficient. And keep in mind that the coefficient represents the significant digits in a number. And also keep in mind that you always put the decimal after the first significant digit for the coefficient right here. Okay, so and we always multiply by the base, and the base is always in this case going to be 10. And when we are converting a number in standard or decimal notation to scientific, we use two basic steps. Okay, so let's talk about those two basic steps. The first basic step that we have is when you have a positive power of 10, that indicates that you need to move the decimal to the left. So in this case, we have this example right here. So let me rewrite it. And this is 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2. Okay, so notice that our decimal is right here. Now we are going to move our decimal to the left, and we are going to count the number of times that we move the decimal to the left. And keep in mind that we want to keep that one first significant digit. So 1, 2, 3, 4, 5, 6, 7, 8. So we're going to move our decimal place 8 places. Also keep in mind, since we did move it to the left, that we have a positive sign. And since we moved it 8 places, we have number 8 as our answer, as our exponent. So that's where the 8 comes in, right here. This is going to be our exponent. Okay? So the next one is whenever you have a negative power of 10, that indicates that the decimal moved to the right. Okay? So over here we have our example. And we're going to take our decimal and we're going to move it to the right here. Now when we move it to the right, keep in mind again that we want to put the decimal after the first significant digit. So it's going to be right after this one right here. So we're going to count the number of places that we move the decimal. 1, 2, 3, 4, 5, 6, 7. Since we moved our decimal to the right 7 places, it's going to be a negative 7. And that's where we get our negative 7. Right here. Okay, so this will be our exponent. We're going to write a positive 8 on the example above. So this is our exponent. Okay, now moving on with this, we want to convert the numbers from standard notation to scientific notation. So again, you guys, here are your two examples. You have 238,900 miles, and you want to convert that to scientific notation. Well, keep in mind where your decimal is and the fact that you want to move your decimal now to the left. So our decimal is right here, and we're going to count the number of places we move it. 1, 2, 3, 4, 5. Since we moved our decimal 5 places to the left, that indicates our exponent. And we're going to keep all the other significant digits. Keep in mind, you guys, that we want to have at least that one significant digit right here. So our answer will be 2.389 times 10 to the 5th miles. we have our next example right here. And in this next example, we're going to move our decimal place to the right. So we're going to keep it up to one significant digit right here. So we're going to count the number of spaces that we move. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is where we're going to move it. We moved it 10 places, so it's actually a negative 10. So this will be our exponent since we moved our decimal place to the right. And that's our answer right here. Okay, so now going back to your notes, let's talk about how to convert from scientific notation to standard notation. Okay, so we're going to go work backwards now. So we have our question right here. The hydrogen-oxygen bond in water is 9.584 times 10 to the negative 11th meters. So we are now going to convert that. Because it is a negative 11 right here, we are going to move our decimal place to the left. Okay, so I'm going to write here 9,584. And our decimal is right here, and I'm going to move it to the left to get it back into standard notation. So basically what you are doing is that you are doing the exact opposite of what you did to convert it to scientific notation. Now we're going to go in the opposite direction. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we're going to put our decimal right here. And that should mean that we have 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the 11th place is our number. And that's what we have for our answer. Okay. Now let's look at this, where Mount Everest has a height of 2.9029 times 10 to the 4th feet. So because this is a positive 4, we are now going to move our decimal to the right. So I'm just going to count the number of spaces. 1, 2, 3, 4. And so our answer is going to be 29,029 feet. Okay. So notice we moved here, 4 is our exponent, we moved 4 places. And over here we have the carbon atom weighs 2.0 times 10 to the 23rd grams. Now notice that it is a negative 23 in this case. Notice that it is a negative 23 in this case, and we are now going to move our decimal 23 places, but now to the left. So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So we moved 23 places. And of course you can put all those zeros, but here is our answer right here. Okay. Okay, so we just talked about scientific notations, but let's go ahead and talk about scientific notations and how to perform certain functions. So I have this paper right here. Go ahead and copy these examples down, and we'll go over it. So how do you add and subtract scientific notations? Well, the way you add and subtract scientific notation is by making sure that the same exponent, that you have the same exponent. So here I have a practice problem. 7.93 times 10 to the 6th plus 5.21 times 10 to the 4th. So we're going to notice that both of these quantities are a different exponent. So we need to convert one of the quantities to the other exponent. So I'll go ahead and convert this. It's usually a lot easier to convert the higher exponent to the lower exponent. So I need to convert this. There's a difference of 2, so I'm going to end up moving my decimal right here 2 places. So it is going to come out to be 7/93 3, and now that's where my decimal is. So I moved it 1, 2 places. Times 10 to the 4th now. Okay? And I'm simply going to add this to my other quantity, which is 521 times 10 to the 4th. So I'm going to rewrite it to you so that you can actually see it. So it'd be right here, 793. This would be 5.21 times 10 to the 4th times 10 to the 4th. You're going to add that up, and so you're going to get this as your answer. Okay, so notice over here how we have the exact same exponent. But keep in mind, you guys, that we want our answer to be in, we want to put the decimal after the first significant digit. So we're going to move this decimal back here, and every time we do, we simply add it up, increase the number of exponents. So that's going to be 7.98 times 10 to the 6th. Okay, so that'll be our answer for this. Actually, you want to cross that, it's going to be 7.98.21 times 10 to the 6th. Okay, so I just simply forgot the decimals. Okay, now moving on and talking about multiplication of scientific notations, you are going to add the exponents. So notice that in this problem you have -2 as the exponent for the first quantity and -7 as the exponent for the 7th quantity. So what you're going to do is you're simply going to multiply the coefficients together first. And when you do multiply the coefficient together, you get 44.5. Now you're simply going to just add your coefficients together. So -2 plus -7 will give you a -9. Keep in mind again that you want to put the decimal after the first significant digit. So you're going to move your decimal 1 place. So that's going to be 4.45 times 10 to the -8 this time. Since you are making your number bigger, it's going to be a -8 this time. Okay, so moving on to decimals. Division. Division of scientific notation, you are going to subtract your exponents. So you have this question, 6.3 times 10 to the 11th divided by 3.0 times 10 to the -3rd. So once again, you are going to divide your coefficients, and when you divide your coefficient, you get 2.1. And then don't forget that you are going to subtract your coefficient. So when you subtract it, it's really 11 minus -3. So in this case, this -3 will cause everything to become a addition problem, and your exponent is going to be 14. So in this case, your answer is 2.1 times 10 to the 14th. Okay, and there's no need to move your decimal because we already have the first significant digit right here. Okay, so let's move on to the metric conversions. So if we go on to your notes, go ahead and go on to the second page of your notes. Okay, so let's talk about the calculator. And we have actually talked about this before, but I want to remind you that whenever we input exponents into the calculator, that you are using that second E function. Never just enter times 10 or use that caret function that you have. So I'm going to use the calculator that's here in our graphic, but you can, the same rule applies. If you have a graphing calculator, the exact same rule applies. So whenever you are using an exponent, right above the number 7 here, you have this x minus 1. And if you look right above the x minus 1 in blue ink is written EE right here. And I can zoom in. That helps you. So if you can see that EE, that's right here. Okay. So what you're going to do in order to get your exponent, you are simply going to write your number. So let's say I have this number times 10 to the 23rd. Okay. So let me move it over. I have this number. I am going to input 6.02 into the calculator. And then this right here times 10 is going to be in your calculator replaced by second, and then right above the number 7, press that. And the E shows up. And now all I have to do is put 23 in the calculator, my exponent. This E right here actually takes the place of times 10, and now it will use this entire quantity. It will actually see it as a single quantity rather than taking your coefficient and multiplying by 10 and then raising it to the 23rd power. Okay, so that is just basic calculator skills that we have. And so let's talk about the next thing is the metric conversion. So in 1960s, a group of scientists actually got together and they wanted to have a common measurement system that was going to be used around the world. So they call this system the SI system, and of course this is the French term for it. So this below right here is a common base unit that's used in chemistry. Keep in mind that this is not, we use a lot more bases than this, that this will be ongoing for you, and definitely this chart will increase by the end of the school year. So right here, you really want to know this, and I'm sure you already do know this, but there are some things that I want to bring your attention to. One right here, keep in mind that there is a difference between lowercase letters and capital letters. So in this case, this is a capital K value. Okay, this is a capital K, and I'll make it there, a capital K value. So lowercase and capital letters do make a difference as far as writing the bases correctly. So let's talk about base prefixes. Okay, so the base prefixes now is in order to use the numbers that are reasonable scale in laboratory settings, we use a set of prefixes. So let's face it, in chemistry, you're either using really large numbers or you're using really small numbers, because we're talking about the subatomic world, or we're talking about the world of atoms. And so you need to have something that puts everything at a reasonable scale. So we came up with something called the SI prefixes. As far as you are concerned, you do need to memorize these prefixes. So you really want to know these. So you want to know this. Can't emphasize it enough that if you don't learn this, you're going to have a really hard time with chemistry math. Okay, so let's move on to the next page. Okay, so if we move on to the next page, right here, I'm going to go ahead and highlight. I'm going to take my marker, and first of all, this space where there's hardly anything written, I am going to highlight this area a different highlighter color. And then I'm going to take another highlighter and highlight the other parts, starting with mega, because you are actually responsible for knowing going mega, kilo, hecta, and deca, knowing this, your base, and then knowing deci, centi, milli, micro, and then pico, nano, and then of course pico. Okay, so you're responsible for knowing this. The reason why I wanted you to highlight one of those colors in a different, one of the prefixes in a different color, is because this is where your base actually goes. Okay, and keep in mind that for your base, when we are doing the metric conversion, your base is always going to have the quantity, when we're doing the conversions, 1 times 10 to the nth power. So it's always going to have that conversion. Okay, so right here from mega to deca, we're going to give it the conversion value of 1, and from deci to pico, we're going to give it the conversion value of 1 also. And I'll explain to you in a second what that actually means. But take some time, and you want to memorize this. If you don't memorize this, you're going to have a really hard time with the chemistry math, because we are converting back and forth between this all the time. Okay, so you really do want to know your conversions. So let's do some practice problems for knowing your conversions. And let's see. Got a piece of paper right here that I'm going to write on. So you've got your conversions that you have. First conversion is from 1 megameter. We want to figure out how many meters is that. So what you're going to do is megameters right here, and you're going to your base meters. We keep in mind that your base will always be 1 times 10 to the nth power. So in this case, because it's mega, it's going to be, we're going to say 1 megameter is equal to, in our conversion factor, we're going to say is equal to 1 times 10. And you have this exponent right here where it says exponential factor. Well, this is the exponential factor for the base. So 1 megameter actually equals 1 times 10 to the 6th meter, which makes sense. So 1 megameter equals about 1,000,000 meters. That makes sense logically. And let's do another one. Let's do, we have here, let's see, 1 times 10 to the negative 12 grams is equal to how many picograms? Well, here's pico right here. And keep in mind that a pico is 10 to the 12th grams. So if we're saying that our base, our gram is 1 times 10 to the negative 12th grams, then we are actually saying that this is equal to, in reality, 1 picogram. Okay, so that's just a few examples that we have. We can do another one. If we have 1 millimeter, how many meters is that? Okay, in our conversion. So if we are dealing with that we can say that we have millimeters right here. Our millimeters is 10 to the 3rd. So 1 millimeters is actually equal to 1 times 10 to the negative 3rd meters, which makes this meters really very small. We could do the same thing with another one, another problem. We can say that we have 1 times 10 to the 3rd liter is equal to how many kiloliters? So in this case, how many kiloliters? We're looking at kilo. Kilo is 10 to the 3rd. So we have 10 to the 3rd liters is actually equal to 1 kiloliter, which makes sense. A lot. Okay, it makes a lot of sense. That 1,000 liters will equal to 1 kiloliter. And so that's how we do the metric conversions. Now let's talk about dimensional analysis. Okay, let's talk about dimensional analysis. Dimensional analysis is the only way to do chemistry math. And we're going to use a very simple concept of metric system conversions to talk about dimensional analysis. I realize you guys know how to do the metric system conversion by moving the decimal around, but I'm using a simple concept today to teach you something difficult, okay, which is dimensional analysis. It's really not a difficult concept once you get the hang of it, okay? So let's see if you can, I'm going to give you some rules on how to set up a problem using dimensional analysis and how to go about performing a dimensional analysis, using dimensional analysis to solve a problem. So dimensional analysis is also called the factor label method, and it is solely based on the fraction format. Okay, so real quick, I want to review with you some fraction rules that you have. So you probably know how to do this already, because these are just simple rules that you have for fractions. So here's a question, 2 of 3 over 2. Now, you know that I could either write this 2 in fraction form as 2, or I could write it as 2 over 1. Both ways are correct. You also know that this of sign means multiplication. So I could write my multiplication sign right there. But in chemistry, instead of writing a multiplication sign, since we know dimensional analysis is solely based on the fraction format, what we do is we draw this horizontal line a little bit longer, and then we simply draw a vertical line. This vertical line actually represents the multiplication it is the multiplication symbol in dimensional analysis. So the multiplication sign or this vertical line mean the exact same thing. You can perform dimensional analysis if you'd like using multiplication, but this is the preferred method by just drawing that line. And then if we're talking about fractions, this actually does look like a fraction. So we can put 3 over 2 right here. And you guys know if it is 3 over 2, then you know that what you're going to do is you're going to multiply the numerators and you're going to multiply the denominators. Over here you do know that there is an imaginary 1 that is present. So 2 times 3 is 6, and then 1 times 2 is 2. You do the exact same thing under dimensional analysis. You just simply multiply the numerators and the denominators, and then you divide at the end. In this case, your answer will be 3. And it doesn't make a difference whether you write 3 or 3 over 1. It is understood to be the exact same thing. So going back to this problem, I have 2 over 3 over 2. And I purposely do not write a 1 here because it is understood. And your math is advanced enough where you don't have to necessarily multiply the tops and the bottoms. What you can do is that you automatically know that you can cancel. So you can cancel or reduce diagonally. You can never reduce in this way. Can never reduce straight across in the numerators. That's a big no-no, and you know that. Well, the same is true for dimensional analysis. You can only cancel units diagonally. Okay, so knowing these few rules of fractions, let's go back to dimensional analysis. Okay, so if we go back to dimensional analysis, the first thing that I want you to write over here is that you are going to always follow units. Dimensional analysis is basically, it's a unit conversion method, and it's going to write universal here, but it's units. Okay, so units. So you're going to follow the units, and you're only going to cancel diagonally. Okay, so you're only going to cancel diagonally. So in this case, let's start off with the problem that is given to us. So in this case, convert 75 milligrams to meters. This is what's given to us, and this is what we need to find. Always start your problem off with what you were given. So in this case, we are given 75 millimeters. And we are asked to find meters. So you're going to go back to your metric prefix chart, and we're going to see what the conversion is between millimeters to meters. Remember that 1, since it's millimeters, we're going to put 1 millimeter is equal to, and our base is always going to have 1 times 10 to the, in this case, because it's millimeter, it's going to be to the -3rd meters. So this is the conversion factor that we're going to use for this problem. So if we have this problem, 75, I'm going to keep it, put it in our fraction form in dimensional analysis. I could put a 1 over here, and if you feel more comfortable, you're more than welcome to put a 1, but just realize that there is a 1, it's just understood. So over here we want to figure out how how are we going to write our conversion factor? So this is the conversion factor that we have. Each one of these quantities is going to be placed in one of the spaces. So we have two quantities and we have two spaces. We can only put one quantity in one of the spaces, in each of the spaces here. So since we want our answer to be in meters and we want to cancel out millimeters, we're going to put millimeters down here. And so if we've got millimeters down here in our quantity, we're going to put the number 1, and notice that it equals this right here for the meters, so that's going to go on top to the -3rd meters. Okay, so now we can cancel diagonally, and the unit that we have left over is the unit that we have. So in this case, our answer is 0.075 meters. You're going to multiply the top and then divide by the bottom, and in this case, since it is 1, I really don't need to divide it. So 75 millimeters is actually equal to 0.075 meters, which conceptually makes sense. Okay? Now let's go down to our example problem, our second example problem. We have here 25 liters, and that is what's given to us, and we want to convert to kiloliters. Always start your problem off with what you were given. Okay, liters. And realize that this is an imaginary one. Now going back, we're converting from liters to kiloliters. So going back to our chart, here's kiloliters, and this is where liters is. So keep in mind that we have 1 kiloliter is equal to, and our base, in this case, because kiloliter is 10 to the 3rd, our base is going to be 1 times 10 to the 3rd liters. Okay? So we're going to take this quantity, these two quantities, and we're going to write it down here. We have liters in our given, but we want our answer to be in kiloliters. So we're going to cancel liters. The only way we can cancel liters is by putting liters down here. So we're going to put liters down, and this is the quantity that we're going to write right here. 1 times 10 to the 3rd. Okay? So 1 times 10 to the 3rd, and on top we're going to write 1 kiloliter. Okay, so now we can cancel diagonally, circle the remaining unit, and our answer should be 2.5 kiloliters, which conceptually makes sense. 2,500 liters is actually equal to 2.5 kiloliters. Okay, so I'm going to do the other examples. And you can do the examples on your own and look up once you are finished to check your answers. Or you can certainly pause the video. Okay, so let's go over this problems really quick. The first one, we're converting 17 grams into milligrams. That's what we're trying to find. Always start off with your given is 1.7 grams right here, and we are going to convert from grams to milligrams. So you're going to use your chart right here. This is your base or your grams, and you're going to milligrams, which is right here. Keep in mind that your base is 1 times 10 to the negative 3 is equal to 1 milli. And that's what we have here. We have 1 times 10 to the negative 3 in the denominator, and we have 1 milligram on the top. So how do you actually input this into your calculator and get your answer? So what you're going to do is in your calculator, you are going to put 1.7, and don't forget that you're multiplying the top, so you're going to multiply by 1, and you get 1.17, and then you're going to divide by your denominator. In this case, it's 1 divided by negative 3. And when you do, you get your answer to be 1700. And I think I didn't put it into my calculator correctly in the first place. So let me fix that. 1700 milligrams. Okay, which conceptually makes sense. Now 1.7 grams is actually equal to 1700 milligrams. So conceptually it's got to make sense also. So let's go ahead and check the next problem. We have 1.95 times 10 to the 7th micrograms. This is too big of a number. Errors could be made, you guys. Make sure that you put it in scientific notation before you even start putting the problem into the calculator to work it out. Too many zeros, you can forget a zero or something and make a mistake. So we want to convert our micrograms into grams. That's what we're trying to find. Keep in mind that you have micrograms right here and grams right here. So 1 times 10 to the negative 6 grams will be equal to 1 microgram. And that's what I have. 1 microgram is equal to 10 times 10 to the negative 6 grams. We want to cancel micrograms, so micrograms will go on the bottom, and our conversion and grams will go on the top. You want to put this into the calculator again, you guys. So let's clear this, and we want to put 1.95. And since this is an exponent, you are going to use that second e times 7, and you're going to multiply. So it's going to multiply this quantity by this quantity, which is 1 second e to the negative 6. Whenever you input a negative, don't use this minus sign. This is the function. You want to use the negative sign instead, and you get 1.5 grams in this case, which makes sense. 1.95 times 10 to the 7th micrograms actually equals to 19.5 grams. And then the last example that we have is 5.48 meters is given to us, and we want to find nanometers. So we're going to start off with what's given, 5.48, and we're going to convert this into nanometers. Since we want to cancel meters and we want our answer to be in nanometers, keep in mind, you guys, for dimensional analysis, the unit that you are solving for is always going to show up in the numerator, okay? And it's the unit that will not be canceled. So since we have meters at the bottom, nanometers will show up at the top. Look, going back to your chart over here, we're going from meters to nanometers. So meters is 1 times 10 to the blank power. How do we know what power it is? We'll go to nano, and under exponential factor it says -9. This -9 is for your base, so 1 times 10 to the -9 meters will equal to 1 nanometers. And that's exactly what I have here. 1 times 10 to the 9 meters is equal to 1 nanometers. The way you plug this into your calculator, again, you guys, is you are going to put 5.48, and then simply, since this is at the bottom, multiply it by 1, you're still going to get 5.48. Then you're going to divide at the end, so I'm going to divide 1, and I'm going to use that second e for 9. Keep in mind, you guys, and I didn't do this, But this is, be very careful, this is a -9. So I need to go back and I need to write a -9 in here. So it's going to be a -9 that I have in the calculator. And my answer comes out very long. So this long answer, I can either keep it as it is or I can convert it into scientific notation. Well, it's too many zeros for me to write, so rather than make an error, I'm going to convert it to scientific notation, and that comes out to be 5.48 times 10 to the 9th power of nanometers. Okay, so this concludes our lecture over scientific notation, metric conversions, and dimensional analysis. Go back and refer to this if you need to for dimensional analysis, you guys, but this is really important stuff. So I hope this really helped you. Thank you.